most emblematic feature in a tropical cyclones. So it can be seen from space. So here you can see the eye of Hurricane Sam, which has been seen from the International Space Station. And in that case, the diameter of the eye is about 60 kilometers. Now, it's important to note that the eye does not only correspond to a region of mostly calm weather, it also corresponds to a recirculation in the vertical plane of the cyclone. Indeed, so here you have the air which moves towards the axis, then maybe I will do it here. Then it rises up in the eye wall, then moves away. So you have a main vortex here. And you can see that there is a secondary vortex here, which corresponds to a reverse circulation and which is associated to a downward motion on the axis of the cyclone. And surprisingly, the origin of the eye, in other words, the origin of this downward motion on the axis, it's still an open question today. So among the different theories which have been proposed to explain this subsidence on the axis, there is one which deals with diabatic heating, so release of latent heat. So in this mechanism, so they consider that the air, the moist air, is rising up in the eye wall. Then at some altitude, the water, which was a gas, becomes liquid. So there is a phase change. And this phase change will be associated to release of heat. And this source of heat at altitude generates a downward motion of the axis. However, the weakness of this mechanism is that it is based on, the reasoning is based on the pre-existence of a convection ring. You can see that more recently, Robert Peirce proposed another mechanism in which the vertical profile of the azimuthal wind, which is called the vortex tilting, plays an important role. And you can see that this mechanism has given rise to a number of exchanges in the weather magazine. So in particular, Roger Smith criticizes Peirce for basing his reasoning on the pre-existence of the convection ring. In other words, he blames Peirce for mixing the causes and the effects in the reasoning. So you can see that Peirce has used his right of reply. And so that story just highlights how the origin of the eye is still today an open issue. So to study tropical, c'est possible d'enlever la barre. J'avais peur de to study tropical cyclones, so we have advanced meteorological models. So among them, for instance, the American model GFS or the European model ECMWF. We have also models which make forecasts over a given area of the globe and which are dedicated to tropical cyclones. So these models include parameters which have been adjusted to reproduce tropical cyclones as well as possible. So these two types of models are based on the mathematical equations. So the equation which describe how the winds, the temperature, the humidity will evolve within the atmosphere. And so in that sense, these two types of models are very different from the third category, which corresponds to statistical models. So these statistical models, they rely on statistical considerations, and they are based on the knowledge of past tropical cyclones. So this third type of model is very different from the other one. We have also simplified models. So we have layered models, so models in which the atmosphere, the vertical profile of the atmosphere is discretized into layers. We have also complete axisymmetric models of tropical cyclones. So these models include several parametrization of the subgrid effects. So for instance, parameterization for convection, turbulence, phase changes. So in that sense, the output of these models is very dependent on the assumptions which have been made in these parameterizations. And so with these types of models, that can be difficult to identify robust physical mechanism. So that's why, in order to investigate the origin of the eye of the cyclone, we decided to construct a fluid mechanics model. That is to say, a model which is totally free of parameterization. So the idea was to model an isolated tropical cyclone. So I mean a convective structure which develops between a warm ocean and the cold tropicaux under the action of the Coriolis force. And so the model we constructed is a rotating Rayleigh-Bénard model written in the cylindrical geometry. It is a model which is axisymmetric. It is written in the Boussinesq approximation, which means that the density of the fluid is considered as constant except in the buoyancy term. And concerning the temperature profile in the model, it corresponds to a stationary profile, so reference profile T0Z, which corresponds to a negative vertical gradient. So it's an unstable profile on which we superimposed a temperature perturbation, so denoted here as theta. And you can see that the domain is elongated with an aspect ratio of 10, as it is the case in a real tropical cyclone. So in this model, we have three variables. So first, the angular momentum, denoted as gamma. We have the azimuthal vorticity, so written as omega phi, so which corresponds to the azimuthal component of the vorticity. So it should not be confused with the vertical vorticity, which corresponds to the main motion of the cyclone. So here we are talking about the azimuthal vorticity, so the vorticity in the azimuthal direction. And the third variable is the temperature perturbation theta. So these variables obey a system of coupled equations. So the first two equations are derived from the Navier-Stokes equation in the Boussinesq approximation. And the third equation here is just an advection diffusion equation for the temperature perturbation. So this system of equations involves three non-dimensional control parameters. So we have first the Ekman number, which is the ratio between the viscous forces and the Coriolis term. We have the Rayleigh number, which is the ratio between the buoyancy forces and the kinematic viscosity and the thermal diffusivity, which both prevent the motion. And the Prandtl number, which is the ratio between the viscous kinematic viscosity to the thermal diffusivity. So we have three control parameters in this problem. Regarding the boundary conditions, so for the bottom plate, we choose a no-slip boundary condition. For the top of the domain, we choose a stress-free boundary condition. And concerning the outer edge of the domain, so it's a bit more complicated because actually this outer wall is something which is totally artificial, because in a real tropical cyclone, it's opened on the atmosphere. So we were first tempted to choose a stress-free outer boundary condition, which is the most natural choice at first glance. However, we have shown by combining simulations and mathematical development that with a stress-free outer wall, that yields a singularity which appears at the external bottom corner here, a singularity which will modify the wall flow in the wall domain. So at the end, we have chosen a no-slip outer wall. Now, let me show you a few steady-state solutions we have obtained with our numerical code. So here I just selected cases when we got an eye. So on this picture, the streamlines, the black line corresponds to the streamlines, and the gray surface corresponds to psi equals 0, so that delimitates the area of the eye. And so depending on the values of the control parameters, we managed to get eyes, but with very different shapes. So now, to understand its origin, let's first have a look at the global dynamics. So on these pictures, I show you first the stream function, then the temperature, and then the azimuthal velocity. And so on this picture, the axis of rotation of the cyclone is on the left. So you can see on the first picture that we have a main poloidal vortex, which is associated with warm temperature on the axis, which is compensated by cold temperature near the external edge. And you can notice that the streamlines near the axis are bended, and that there is a counter vortex, which corresponds to the eye. Concerning the azimuthal velocity, so the total angular momentum is advected towards the axis, so that's traduced by an increase in the azimuthal velocity. And you can notice that it is surrounded by an anticyclone here, which is near the external edge and near the top. And this picture is actually similar to what happens in real tropical cyclones, because in real tropical cyclones, you have the cyclonic circulation in the lower troposphere, which is surrounded by an anticyclone of larger scale. So this picture shows that the global flow is mainly driven by buoyancy and affected by the Coriolis force. Now, let's have a look at the local dynamics. So we get closer to the eye. So in this picture, so the axis of rotation is still on the left, and we superimposed the streamlines in black and the azimuthal vorticity field in color. So blue means negative and red means positive. So as expected in the bottom boundary layer, the azimuthal vorticity is negative. Concerning the eye, so the eye corresponds to a reverse circulation, so it's associated to a negative azimuthal vorticity, and this vorticity is the strongest in the eye wall because that's where the motion is the most intense. So now the question is, where does this negative azimuthal vorticity in the eye wall come from? So to answer that question, we plotted here the evolution of the azimuthal vorticity along a streamline, so which is the streamline which is in white here, which passes through the eye wall. And so on this picture here, the abscissa called tau is just a parametric coordinate in order to know where we are on the streamline. So now let's have a look at the equation which governs the azimuthal vorticity evolution. So what we have done is to superimpose on this figure the evolution of each term of this equation along the streamline. So in black, the inertial term, in red, the vortex tilting term, in blue, Coriolis term, viscous term in green, and buoyancy term in cyan. So first, you can see on this figure that the Coriolis and buoyancy forces are negligible near the axis. Then you can also notice, looking at the red curve, that the vortex tilting term first yields an increase of omega phi and then a decrease of omega phi. And actually, the net balance of this vortex tilting term is 0. It can be shown by considering the inviscid limit. So in fact, in this inviscid limit, so no viscous forces, the gamma, so the angular momentum field, is only a function of the stream function, psi. So that means that if we draw a stream tube like this, that means that the contours of the tube corresponds to iso-gamma line. Now, if we write the equilibrium between the inertial term and the vortex tilting term, so the left term can be rewritten as a divergence between we are in the Boussinesq approximation, so the flow is divergent free. And then we can integrate this equation over the stream tube here. And if we do so, we get that the flux of the azimuthal vorticity through the contours of the stream tube equals the integral of the vortex tilting term over the surface of the stream tube. And actually, this integral on the right can be rewritten as an integral in the z direction at a given r. And since gamma is constant along the contours of the stream tube, this integral is 0. So that means that the flux of vorticity which enters the stream tubes equals the flux of vorticity which leaves the stream tube. So that means that there is no production of azimuthal vorticity by the vortex tilting term. So at the end, the only source of azimuthal vorticity is the viscous term. And so in our model, the mechanism for eye formation at the end can be described as follows. So because of the viscous terms, we have negative azimuthal vorticity in the bottom boundary layer. Then this negative azimuthal vorticity is advected toward the eye wall, where it will then diffuse inside the eye through cross-stream diffusion. And so in other words, in our model, the eye is just a passive response to the accumulation of negative azimuthal vorticity in the eye wall, which itself results from a nonlinear instability. So in this the first version of our model was very idealized. And so we then tried to make it more real, so to get closer to real tropical cyclone. So first we have modified the bottom boundary condition. So we inspired from the bulk aerodynamic formula, which parameterizes the flux, the heat flux, and the momentum flux. And we also implemented through an idealized model the radiative cooling effect, so which corresponds to the radiation of heat towards the upper atmosphere by the cyclone. And by doing that we got eyes with more geophysical shapes. I mean that, for instance, on this figure, you can see that the eye reaches the bottom, which was not the case in most of the simulation with the original version of the model. And that's the case in the real tropical cyclones. The eye must reach the bottom. So now we are implementing humidity and phase changes. So this work relies on the Renyi-Bena setup, which has been derived by Jeff Vallis and Steve Tobias in 2019. And we are also constructing a three-dimensional model for an isolated tropical cyclone. And so this work has been started by Julien Collard, who is doing his Master 2 internship at LATMOS. I will now switch to the second part of my presentation, which deals with the generation of waves by tropical cyclones. So let me first show you what these waves look like. So this video was taken by a sail drone inside Hurricane Sam in 2021. Actually, that's the first ocean video made inside a tropical cyclone. So waves in tropical cyclones can have a height which can reach 10 or 20 meters, and in that case, the cyclone has measured waves of 15 meters high. And so we are interested in the generation of these extreme waves because it's still an open question today. And so to do so, we have first a wave forecasting model. So wave forecasting models are based on the WKB approximation. There is indeed a scale separation between the waves and the ocean. The wavelength of the wave is about 100 meters, whereas the bathymetry and the currents in the ocean, usually they evolve at scales, say, larger than 1 kilometer. So there is a scale separation between the waves and the ocean. And so this scheme summarizes the problem we are facing. So we have waves which are characterized by an energy spectrum, and these waves evolve in a slowly large-scale medium, in a slowly varying large-scale medium, so which is represented here in red color. So that means that at a given location in the sea and at a given time, we have a spectral axis, which are called wave height spectra. And if you take this spectrum and if you average over the spectrum, you will get the total local energy. And if you average over the domain, at the end you get the total energy of the waves. And so the mathematical formulation of this problem involves 4 parameters in space. So we have 2 parameters in the physical space, x and y, and 2 parameters in the spectral space, kx and ky. And the action, which is defined as the ratio between the wave height spectrum and the frequency, is governed by a 4D advection equation with, in addition, source terms. So the advection part of the equation is on the left, and you can see so x dot, which corresponds to the group velocity. So that corresponds to the velocity of the waves in the ocean. And you have k dot, which is like a spectral velocity, which corresponds to the rate of change of the wave number. This rate of change of the wave number, it is related to the inhomogeneities of the bathymetry and of the currents. And on the right of this equation, and so the total velocity field, so which involves x dot and k dot, it's a 4D velocity field, which is divergence free. On the right of the equation, you have the source terms, which model physical processes, like, for instance, the generation of waves by wind, the dissipation of energy due to wave breaking, and the nonlinear interaction between the different waves. And so the wave forecasting models are all based on this action equation. And so Louis Milamont, who is doing his PhD at LATMOS, is now constructing a Lagrangian numerical model, which is based on this action equation in order to investigate waves in tropical cyclones. So to study waves in tropical cyclones, we do not have to use the action equation. There is another option, which is to build simplified models. And so these simplified models, they do not aim at reproducing the full energy spectrum, but they focus on average quantities of the spectrum. So I show you here a wave height spectrum. So for instance, we can average over the spectrum to get the total energy, E dot here. And actually in the community, the quantity which is used is not E dot, but it's what we call the significant wave height. So it corresponds to 4 times the square root of E dot. And this is the quantity which is used because it is in meters and it globally corresponds to the visual impression of the sea state. From this wave height spectrum, one can also derive the dominant direction of the wave. So here, for instance, the dominant direction of the wave is from the southeast here. And the dominant wavelength of the waves, so here, on this spectrum, so the wavelength corresponds to the distance to the center. So here it's a bit larger than 200 meters. So now let me show you what these average quantities look like in a tropical cyclones. So here that corresponds to Hurricane Sam in 2021, for which we have many wave observations. So on this map, you have the trajectory of the cyclone and the location of the different devices which measure the waves in the cyclone. So we have measurements from buoys, from the NDBC network. We have also measurement by the sailboat I mentioned earlier. And we have a measurement by radars. So radars on board reconnaissance aircraft. So that corresponds to the trajectory in black here. And we have also observations of waves by radars on board satellites. In particular, we have the observations by the radar swim of the satellite CFOSat. So you have the tracks of CFOSat here in black. So on this figure, we have gathered the measurements made by the different devices between the 29th of September and the 2 October. So this representation is made in the frame of the cyclone, which means that the cyclone is moving up the slide. And so the straight lines corresponds to measurement by radars on board of aircraft or satellites, and the fluctuating lines corresponds to measurements made by buoys and by the sailboat. So here we are in the frame of the cyclone. So the field in color here corresponds to the significant wave height, so the height of the waves, and you can see that there is an asymmetry, and that the strongest waves are located in the right quadrant of the cyclone. Now let me show you the wavelengths, the dominant wavelengths of the waves. So you can see here that the largest wavelengths are located in the 2 front quadrants of the cyclone, and the wavelength is about 300 meters. And if we do the same with the dominant direction of propagation of the waves, we get this figure. So the strongest winds occurs in the radius of maximum wind, so here, so in the eye wall. So most of the waves come from this area, but you can see that the wave structure is not as simple as a purely radial radiation. For instance, if you look at the right front quadrant here, you can see that globally the waves move forward. They are not moving radially. So it's not as simple as a radial radiation. So the asymmetry of the wave field, it partly originates from the asymmetry of the winds of the cyclone, but they are also due to a second effect, which is called the extended fetch effect of the trapped waves effect. So this effect is described on this picture. So you have a cyclone, which is moving up the slide at the velocity v. And so the waves which are generated in the right of the cyclone, they move forward with the cyclone, which means that they will experience an extended fetch compared to the stationary situation, so a situation when the cyclone is not moving. And by fetch, I mean the time they spend under the cyclone. So waves generated on the right experience an extended fetch because the cyclone is moving forward, whereas the waves generated on the left, they move in a direction opposite to the cyclone, so they experience a reduced fetch compared to the stationary situation. So that means that there is an asymmetry between both sides of the cyclone. So this extended fetch theory has been recently formalized using simplifying assumptions by Kudryavtsev et al. So in 2015, in a one-dimensional model. And so this model is actually an extension of the similarity laws for wave growth. So an extension to a moving frame of reference. I mean the frame of reference of the cyclone. So in the stationary case, the waves generated on the right and on the left, they will just grow in the same way, moving forward or backward. Now, if the cyclone is moving up the slide at the velocity v, a wave which is generated on the right, it will first move backward in the frame of the cyclone because it moves slower than the cyclone itself. And then, when the velocity of the wave will reach the velocity of the cyclone, it will make a U-turn and it will then move forward in the frame of the cyclone. Whereas a wave which is generated on the left, it will just exit more rapidly than in the stationary case, the cyclone at the rear. But the fact is that this U-turn I have just described, it does not always happen. For example, if the cyclone is moving too fast, the wave won't reach, the velocity of the wave won't manage to reach the velocity of the cyclone, and it will just exit the cyclone at the rear. And so this Lagrangian reasoning can be traduced in a system of equations which describes the characteristic of the strongest wave in the cyclone. So by characteristics, I mean the significant wave height and the peak period of the waves. So that's what this system of equations describes. And so now what we can do is to try to compare the observation with this simplified model. So on the left, you have the significant wave height according to the observations. So that's the same figure as the one I have shown you a few minutes ago. So you can see the asymmetry between the left side and the right side. The strongest waves are on the right. And on the right panel, you have the significant wave height calculated using the model I just presented. And so you can see that there are gray areas. So these gray areas corresponds to areas which are not described by the model. They cannot be described by the model because the model is a one unidirectional model. So for instance, in the gray area at the top, that corresponds to waves which were generated on the right of the cyclone, but we are under winds which are perpendicular to the waves. So the one-dimensional model cannot describe this area. So that's why there are these gray areas. So the first observation we can do is that the model is quite good, in particular in the right quadrants of the cyclone, except on this track here, the red track, which is actually quite far from the center, which could be a reason for which it does not work as well, but otherwise, in the right quadrant, it's not so bad. However, you can see that on the left, the model is underestimating the significant wave. And actually, that can be explained by the fact that this is a unidirectional model, and on the left of the cyclone, the fields which are observed are not consistent with this approximation. So what we can do now is to try to investigate the possible existence of trapped waves in the right quadrants of the model, of the cyclone, sorry, using this model. So that's what we have done using the data of the sail drone. So in this picture here, you can see the trajectory of the sail drone in the frame of the cyclone. And so this sail drone, it measured the wind field and the waves, the significant wave height in particular. So this is shown on this figure. So the black dots, the black crosses corresponds to the wind, and the blue dots corresponds to the significant wave height. And the abscissa here corresponds to the distance to the TC center. And we put the same sign as the coordinate y. I mean that if we are south of the cyclone, it's minus. If you are north of the cyclone, it's plus. And so on this figure, we superimposed the value of the significant wave height calculated using the model by taking into account the velocity v of the hurricane. So that corresponds to the red curve. And in black, we did the same. We calculated the significant wave height using the model, but we set the velocity v of the cyclone to 0. So we ignored the translation velocity of the cyclone. And you can see that if we do so, if we ignore the translation velocity of the cyclone, the significant wave height is much underestimated compared to the observation. Whereas if you take into account the velocity of the cyclone, the values are not so different. We are closer to the observation anyway. So that means that the large values of significant wave height which have been observed in the right quadrants of Hurricane Sam are consistent with the extended fetch theory I have presented you a few slides ago. And so this work has been on waves in Hurricane Sam has been done with Xiao Zhao, who was in PhD at LATMOS. He's just back to China now. And I will end this presentation just by stressing the importance of simplified models to understand, to extract physical mechanisms in complex systems. Thank you very much.